Okay, time to get started. Welcome back, everybody. I hope everybody had a good spring break. Proceeding along from where we left off. Before I get into the math, let me just remind you all of a couple things. We do have a midterm exam coming up at the end of this week, right? So I hope you all had at least a little bit of a chance to study math over break. I understand it's hard to, there's a lot going on and et cetera. But anyway, exam at the end of this week. Today is the last day of fair game material for that exam. So everything we do in class today, could be on the midterm. And the stuff that we're going to do on Wednesday won't be fair game. So anyway. Okay, so here's what we were talking about last time. We were talking about symmetry theorems. So in particular, we basically just kind of reviewed this single variable calculus theorem right here, which is that if you have an integral from, negative a to a, right? In other words, if the domain is symmetric when you reflect over the origin. Let's see here. Yeah, so if your domain is symmetric, and if your integrand is odd, and keep in mind what odd means. Odd means that when you negate the input, you also negate the output. Right? Beautiful result with these two conditions checked. That integral is 0. Walk away. You don't have to do any anti-differentiating. You don't have to use the fundamental theorem of calculus, right? It's just boom, 0, end of story. Awesome result. It doesn't really come up all that much in single variable, but it's a really important segue into where it is going to be used a lot. Why does it work? Well, roughly speaking, the point here is that the terms cancel, right? If you look at the term there corresponding to that value, and then you look at the term in the Riemann sum here corresponding to that value, they are negatives of each other because of the oddness. And therefore, every term cancels, and thus we get a total of 0. On the other hand, you can also view it as something you can see from the point of view of a substitution. So all I've done in this argument here is use this substitution, x equals negative u. That's just a substitution. Right? And of course, in order to do that, I have to take advantage of the fact that this interval, by assumption, is its own reflection. Right? It's a symmetric domain, and so it is its own reflection. And then I'm further taking advantage of the fact that the value of the function, after negating the input, negates the output. So you can see exactly how the conditions of the theorem get used. But ultimately, what's doing the heavy lifting, what's really doing the work here, is this substitution, which, of course, keep in mind, they can't say this in a Calc 1 class, but a substitution is really a change of variables. It's just a single variable change of variables. Okay. All right. So with all of this noted, we're going to generalize this to 2 dimensions, which I believe we just barely started on last time, however long ago that was, 10 days ago. It was a long time. So instead of reflecting over the origin, now we're going to talk about reflecting over a line. Let's try to hit that, actually. A line in the plane. There's a lot of lines in the plane, right? So I can't write an explicit formula that we'll always be using for these reflections. It's not as simple as, just multiply by -1. It's not that easy. Lots of different lines we could be reflecting over. But so with that idea that a reflection is exactly what you think it is, we can define analogous ideas of, what do we mean by a function being odd? Again, that just means if you reflect the input, then you negate the output. Perfectly analogous to the single variable version of odd, right? And then likewise, what do we mean by a symmetric domain? And there's different ways to think about this, different ways to write it down. I think the simplest way to think about what it means for a domain to be symmetric over a line, it is its own reflection. So when you do the Rorschach test, right? I mean, when you kind of flip it over the line, it looks exactly the same. Okay, so with that noted, we have a totally analogous theorem. And here it is. Notice I've written it on the page even to look analogous to the single variable version of this theorem. And if your integrand is odd and if your domain is symmetric, then your integral is 0. No anti-differentiating necessary. And in this case, even more celebration, no slicing necessary. No deciding which way to order your differentials and worrying about the cross sections and what's a function of all that, inconvenience that goes into computing a double integral the old-fashioned way. Just 0. Boom. Done. So really, really nice result. Now, a couple of warnings. You do need to have both of these conditions satisfied. All too often, students get a little too enthusiastic about symmetry. I appreciate enthusiasm for symmetry, but you do have to use it responsibly. The mere having a symmetric domain by itself, not good enough. Right? You have to have the odd symmetry of the integrand as well. You have to have both. And the other landmine that students will step on is to fail to use the same line. It's got to be the same line for both of these symmetries. The odd symmetry of the integrand and the symmetry of the domain have to be over the same line. And again, otherwise the argument just doesn't work. It doesn't make any sense. Speaking of which, how does this theorem hold together? I'll go back up to the other point of view in just a second. Let's look at the Riemann sum point of view first. Here's my symmetric domain, my attempt anyway to draw a symmetric domain. Notice this weird shape, kind of a kite-looking thing. Right? It is its own reflection over that line. So it's a symmetric domain. And that being the case, whatever term I have over there will be a corresponding term over here. And the integrand being odd will make these terms negatives of each other. And so in the summation, they cancel. So totally analogous to the single variable result. And likewise, that substitution point of view. Let me say that a little bit differently. The change of variables point of view that we had in the single variable case. Well, a change of variables point of view works here. We literally use the reflection as our change of variables function. So you look at going from this integral to this integral, all I've done is pull back through the reflection. And of course, the thing that makes it work in the first place is the domain is its own reflection. And secondly, if you look at the value of the function at the reflected point, you get that minus sign. So there's where the oddness comes in. And just like in the single variable case, notice what we've argued then is that this integral is its own negative, and that means that the integral must be 0. So really cool argument. Totally analogous to the single variable substitution. Okay, let's get our hands dirty and do one. We want to compute this integral right here, where specifically our domain, right, is this, whatever that thing is. We have here a region of the plane bounded by this chordic and that line. Okay, now at a glance, I think you'll probably agree with me, this is an unappetizing looking integral, right? I mean, look at the integrand, yikes. Exponential with stuff inside of it, I don't know. I'm not enthused. I claim it's worse than that. Because keep in mind, right, the shape of the domain is going to factor in as well. In particular, you're going to have y as a function of x. Your dy slicing will be on the inside. That means that everywhere you see a y, that's going to have a chordic in x. So that's not just going to be an innocent little y sitting there. That will eventually be a chordic in x. And so you're going to have this really ugly integral to deal with here. So we don't want to do that. Okay, let's draw a picture of our domain. See what we're actually up against here. Let's see here. I'm going to try to draw it over here. Let's talk about that curve right there. Flashbacks to Calc 1, right? Curve plotting. A bunch of stuff to say about that, but y'all know how that works. I like to think of this as, well, I can see that there's a parabola from this x squared term, and I can see that there's a vaguely parabola-like thing, superparabola, perhaps. This chordic term here. And between the two of them, good exercise to make sure you can persuade yourself of this, but it ends up looking something kind of like this. So give yourself the time as needed to think that through and confirm that that's what you get as well. Then let's see, this line, y equals -1, of course, is something like that. So our region, where we're actually doing our integral, the region that's bounded by these two curves is this shape right here. And I'm going to make a hand-wavy geometric appeal. That's a symmetric domain. Right now, if you don't feel comfortable with that argument, I do have a more explicit argument down here. You're not going to be required on my tests to make any sort of algebraic justification of why the domain is symmetric. But the big idea here is that if I look at what happens when I literally reflect over that line, right, there's our line of symmetry for this domain. Well, here's the explicit formula for how to reflect over that line. If you have some point, its reflection, you see right here, reflection is going to have the same y-coordinate as the original point, right? But the x-coordinate of the reflected point will be the negative of the x-coordinate of the original point, and that's this point side. And then, quick observation, if the act of reflecting is only going to introduce a minus sign onto the x-coordinate, you can just plug that right into the curve and notice that this original, the reflection of our original purple curve, algebraically identical to that original purple curve. So it is its own reflection, and so likewise the shape underneath it. So this is just to persuade you if you thought you needed it. But again, you don't have to write this kind of stuff. Yeah. Okay, so we have a symmetric domain. Now we have to check and make sure that our integrand has the odd symmetry that we're going to need as well. Let's see here. Let me reduce to what we need. We no longer need the domain. We've already addressed that. Is the integrand odd? Here is our integrand. This is our function f. That's what I need to know. I need to know if I plug in this reflection here. Reminder, there's my formula for my reflection. And you can see me plugging that reflection into the function right there. Do I get a minus sign? Right? That's what it means to be odd. So here I go. I'm about to take this formula for the reflection, noted previously. I'm going to plug into that function. This does get a little confusing. You've got to be a little bit careful with this. The whole idea here is that what I'm going to plug in for my first coordinate, which is going to look like x up here, I'm going to be plugging in minus x in place for the x. That's what it means to have minus x as my first input. So that minus x is going to go there and there and there, like so. Right? And then we're also going to have y. That's going to go where the y is, because y doesn't change. And then I've just got a little bit of an algebra problem here. And, of course, y'all are experts at algebra. Does this kick out a minus sign and, yada, 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 algebra? Make sure you can do all that, right? Got to make sure you're slick with the algebra. And sure enough, we do indeed get the minus sign that we need. So our integrand is odd. Everybody on board? So this brutal integral, right? This nightmarishly inconvenient integral, 0 by symmetry, walk away. No fuss, no muss. Everybody happy with that? All right, it's a really slick trick. My own personal opinion is that symmetry arguments are underappreciated in multivariable calculus textbooks. I think they're bonkers useful. And I cite just, my own experience. As I did this second major in physics, whatever that was, I was in college. I did countless integrals as part of that major. And a lot of y'all are engineers, and you're going to be doing countless integrals too, right? So my estimate, just ballparking from memory, is that about 20% of the integrals that I encountered in my physics travels were 0 by symmetry. And so knowing this trick, knowing how to use symmetry theorems, cut down my, integral liability, right, by 20%. That's awesome. That makes it one of the best, if not, it's certainly in the top 2 or 3 best integration techniques that I have ever seen. So I think it's extremely important. And again, a lot of textbooks undersell it and underdiscuss it. Now, y'all have heard me say a million times that this is not a class about answers. This is a class about reasoning and ideas, right? So as you know, if you're going to use a line of reasoning, well, you've got to explain that line of reasoning, like on a test or on a homework exercise or whatever. So I want to document, just to remove all possible ambiguity, what I consider to be a complete symmetry argument. And it has 5 required elements. You got to tell me what line of symmetry you're using. Again, there's lots of lines. There's lots of lines that someone might attempt to make a symmetry argument through. So you got to, make sure to tell me which one you're using so I know what you're talking about. You're going to need the formula for the reflection, so you have to write that down explicitly. You have to state correctly that the integrand is odd. You have to show that the integrand is odd, just like we did in that last example. And you have to state correctly that the domain is symmetric. Now you'll notice, conspicuously absent, you do not have to demonstrate that the domain is symmetric. You have to state it. Right? You got to doff the cap to how important it is that the domain actually be symmetric. Otherwise the argument crashes and burns. And you got to be right about that. You can't just go around claiming stuff is symmetric if it isn't. But you don't have to prove it. So this is what I want to see in what I'm going to call, if I require a complete symmetry argument. And go ahead and assume that I'll be requiring a complete symmetry argument. Okay, how are we doing? Okay. All right, several more examples to come. I do want to give you a warning, though. It's just an unfortunate reality, but if you try to use a symmetry argument and it doesn't work, unfortunately what that means is that nothing you've written down is actually part of or in the direction of an actual valid solution, right? So there's a risk there. If you try to make a symmetry argument work, and if you inadvertently get one of these arguments wrong or something, right? And therefore you thought there was a symmetry argument, but it didn't work. Well, again, if there is no symmetry argument to be made, then a wrong symmetry argument is not progress toward a solution. It's progress toward a dead end, right? And so it's just from a partial credit point of view, it's irrelevant to the actual solution. So that's the danger. The danger is if you're a little bit too casual with your symmetry arguments, you might accidentally talk yourself into missing any opportunity to put down a valid solution, right? And so you got to, kind of be careful with yourself about that. And please double check, right? If you're going to use a symmetry argument, be careful. I mean, frankly, it's so much easier to use a symmetry argument when it actually works than cranking it out the old-fashioned way, it's still a big effort and time saver. Don't get greedy and try to save even more time by doing it carelessly. Okay, so heads up on that. All right, moving along. This next example, now this is going to appear at first glance to be a reasonable response to an exercise. Here's the exercise. Here is a student response, hypothetical student response. And, the domain is symmetric. You can see the domain right there. Domain symmetric. Not hard to see. This integrand, the student is asserting here that has odd symmetry, and side note, it does have an odd symmetry. And then the student says, well, the integral is equal to 0 then. But let's think carefully now about how much of the required argument has been included here. If I can get my thing to cooperate. Here we go. So this student has not indicated what their line of symmetry is. You say this domain's symmetric, yeah? Through what line? Side note, there's 4 lines that domain is symmetric over. So I don't know what you're talking about. If you just say it's symmetric, that leaves a lot unstated. It's not clear what this means. Is that cool? Everybody see the gripe? Right? Okay. The student has not written down the formula for the reflection. Now, the student has correctly indicated that the function is odd, but the student didn't demonstrate it. There's no indication of why this is odd. And any such indication, of course, would be an algebraic calculation that would have to use the reflection that the student hasn't written down, which would depend on the line that the student hasn't indicated, right? There's some huge gaps in this work. And of course, the student did cite the symmetry of the domain. So this student's done about 40% of what I would call a complete symmetry argument. And, scoring would be roughly proportional to that. So keep in mind, don't be fast and loose with your symmetry arguments. Make sure to give me all 5 of the required elements. Does that make sense to everybody? Homework and exams. Okay. I'm going to make one last comment about this, and that is that, this business about giving me a complete symmetry argument, including all 5 of these elements. When it comes time to the final exam, there's a case to be made that, when we cite these kinds of arguments, there's usually other stuff going on. And we have a long practice in this course of relaxing that requirement in some form or another on the final exam. So I can't be precise about that just yet because I'll have to talk with the other instructors and we'll have to kind of negotiate what we think would be a nice sort of compromise. But on the final, let me just sort of say probably not going to be requiring all 5 of these. But for exam 2, all 5, complete symmetry argument required. Okay. Is everybody good? Or am I moving? I know I'm moving real fast, but everybody's happy. Yes?
I just have a quick question about the reflection.
Yep.
So in the example, say we said the line of symmetry was on the x-axis, it was x equals 0.5, it was
how would you reflect over such a line? Yeah, that is a tricky one. There is a clever argument that you can make there. Let's see here. Oh gosh, you know what? Let me just abandon that whole thing. Okay, here's the clever argument. If you want to do a reflection over that line right there, x equals... Oh, why won't that... What's going on here? Did my pen just run out? Oh, come on. Sorry. Man, my pen just ran out. I'm sorry. Give me a second. Gotta plug this in. Okay. All right. Okay. So, reflecting over x equals a. Here's the slick move. If this point has x-coordinate. Let's call that, well, I'll just call it x, actually. Its reflection over here by symmetry, this, I'm just going to call this question mark. I don't know what that coordinate's going to be, but I do know that this is a reflection. That means it's going to be kind of a symmetric picture, and one way to say that is the average of x and question mark will be a. And so, roughly speaking, x plus question mark is going to equal to 2a, and then you can solve for question mark. Does that make sense? Yeah, nice little move, yeah.
But for the problem you were showing, the one with 0 to 1, 0 to 1, this would not be a valid symmetry because of the odd requirement, right?
Oh no, there is a valid symmetry argument here.
No, I mean
yeah.
the line A on x-axis, right?
Yeah. Correct. Yeah, if you tried to make a vertical symmetry argument for this example, it would fail. In particular, the integrand would not be odd.
Or this one would have to be x equals y? The line?
Yeah, I think that's the only one that'll work is y equals x. Yeah, absolutely. Yeah. A lot of nice details to think through there. Y equals x is the correct line of symmetry, so you want to think that through. Okay, cool. So, here's the next example. This is a nice example of how to find tricky reflection formulas. So here's our domain. I think it's I wanted to be in highlighter mode here. This domain, I think it's a pretty easy pitch that looks kind of like this. Make sure that you are good to go with understanding these kinds of lines and curves and drawing the picture and thinking through that that's your domain. And now I'm just going to make an intuitive appeal that I think should go over okay, that this is symmetric over that line right there. And again, you don't have to demonstrate it, right? It's usually pretty clear from looking at a reasonably accurate picture. If it's true, that is. It's usually reasonably clear that a symmetric shape is symmetric. Okay, so how do I find the formula for the reflection? And looking at that line, now let me zoom in over here so we can see. Oh, come on, here we go. There we go. So the reflection, if I take this point right here and reflect it to that point right there, it's kind of hard to think through exactly because how far you've gone in this direction changes. This is not a simple matter of it's just really not clear exactly immediately how you do this. But take a look at this rectangular frame. I think it is pretty clear how rectangular frames reflect, because this is a 45-degree line, and horizontal will reflect to vertical, and vertical will reflect to horizontal, right? And that makes for actually a pretty convenient way to describe this reflected point. The reflected point, well, there's its x-coordinate, and there's its y-coordinate. So negative y comma negative x, and you can see over here that is indeed our formula for our reflection. Negative y, negative x. Is everybody happy? Okay. All right, so again, you do have to confirm that the integrand is odd. So again, we're going to be doing this weird thing where we're going to take our function. Here's our function f is this thing. It doesn't quite fit, does it? There we go. We're going to take this function, right? And now we're going to plug in the reflection. Let's see, we already wrote down the reflection. Here's the reflection. Negative y comma negative x. When I plug in negative y comma negative x into that function, notice my first coordinate is negative y. That means the negative y is going to go where the x was. Which means that, for example, this minus y is going to go there and there, like so. right? And then likewise, let's see, oh gosh, I'm using a lot of colors here. I'll use red. Then the negative x, being my second input, is going to go where the y was. So that negative x goes where that y is and where that y is, like so. So be careful with the plugging in, right? You got to think it through. And the nice punchline then is that when you write that down and you simplify, and you got to, there's some algebra to be done there. So again, think it through, check the algebra, make sure not only that you can follow this algebra, but make sure you understand how you could do this independently on your own. And as required, let's see here, we have that the reflected output is the negative, as it's supposed to be. So, symmetric domain, odd integrand, integral of 0 by symmetry. Everybody happy? All right, now here's the landmine. Here's the very dangerous thing that I don't want y'all to step on. And let me try to talk through why I think this is dangerous. If you look at how this question is stated, well, I mean, I'm just all sorts of prepared to believe that this is an odd function. It's got an odd exponent. And in fact, you know what? This is an odd function in a certain sense. Right, over a certain line, yes, this is odd. And then you can look at your domain, and your domain here has, let's see here, the vertices are like this. So our domain is like that, and that triangle is symmetric. So it's very tempting to say odd integrand, symmetric domain, integral of 0 by symmetry, and you spike the football and walk away. And get 0 on that question because a little too fast, a little too careless with the details. The integrand, the reflection that would allow this integrand to be odd would have to reflect over the x-axis. I would need a minus sign to show up here. I would need y to reflect to minus y, which would be through the x-axis. But my domain here is only symmetric through the y-axis. So even though, I do have a symmetric domain and I do have an odd integrand, they use different lines. So there is no symmetry argument. Any attempt to make a symmetry argument is a dead end and isn't progress. Does everybody see what the problem is there? Everybody see why this is so dangerous? Right? Very dangerous. I've seen lots of students mess this up and get in trouble. Okay, so careful. By the way, just at a quick glance, it's actually immediately clear that this could not possibly be susceptible to a symmetry argument because the integral is obviously not 0. This y is never negative. The y is always positive for this whole domain. And if your integrand is always positive, there couldn't possibly be any cancellation. This integral can't be 0, and therefore can't be 0 by symmetry. All right. Moving along, 3-dimensional symmetry arguments is extremely similar. It's practically the same idea. The big difference is that now, instead of not being in 1 dimension but 2, now we're not in either 1 or 2 dimensions but 3. But it's still the same basic idea of what we mean by reflection. We're reflecting through a plane now instead of a line. That's morally kind of equivalent. We can still talk about what we mean by odd, and odd symmetry means that when you reflect the input, you negate the output. Okay. And we can still talk about what we mean by a symmetric domain, And again, there's different ways to write this down. I think the easiest one is to just say that a domain is symmetric if it is its own reflection. And with all of that stated, we get the exact same, morally anyway, exact same theorem. So again, deliberately writing it to be analogous, to look on the page analogous. If you have an odd integrand and a symmetric domain, then your integral is 0. Same two qualifiers. You do have to check both conditions, right? Again, one is no good. Just having a symmetric domain by itself tells us nothing. Okay. And likewise, it's got to be the same plane. As we saw in the last example, right? If you're using two different planes to check these two conditions, then the whole thing crashes and burns. Doesn't work at all. Couldn't possibly work. Doesn't make any sense. So, heads up for that little detail again. Okay, same basic ideas though, same argument. In fact, I think it'd be a nice little exercise. Ask yourself, how would you go about proving this? Right? You can try to reproduce the Riemann sum argument, and you can try to reproduce the change of variables argument. It goes down very, very analogously. Okay, so let's see an example in action. Let's compute this integral right. Let's compute this integral right here. It doesn't look that bad at a quick glance until you notice that the domain is the unit ball. And remember, when you slice up the unit ball, square roots everywhere. Right? So this is a nightmare of an integral. And then you might say to yourself, oh, yeah, okay, fine, but I'll do this in spherical coordinates. Okay, you can do it in spherical coordinates. And you're going to have lots and lots of trig to play with. And not that it can't be done, but that's still pretty inconvenient. Okay. So, instead, I am going to make a symmetry argument. Rather than walk through the symmetry argument as written, I want to walk through my rationale for where I came up with this symmetry argument. In particular, I'm going to try to explain, first of all, why did I decide to use the xy plane? After all, you look at your domain here, the unit ball. The unit ball is symmetric through like all the planes that contain the origin. That's like infinitely many planes. Why am I using this one specifically? So here's my rationale there. So it's all wishful thinking, frankly. And so I'm going to start by looking at my integrand, and what leaps off the page at me is that 3 right there, because that 3 is odd, and odd exponents make me think odd integrand, and that's what we're looking for, right? So, okay, so fine. So that 3, I'm going to try to capitalize on this 3. Okay, so that means that I want in my, when I'm doing my calculation to see if the function actually is odd, I want z to be attached to a minus sign so that that minus sign will get cubed and give me the resulting final minus sign that I need. So because of that 3, I'm hoping that I can find a reflection that'll look like this. Wouldn't that be nice? Wouldn't it be nice if my reflection just put a minus sign on the z, then that minus sign will get cubed, I'll get the oddness that I want, and life is good. Okay, again, wishful thinking, right? I mean, I'm hoping that this 3 can make the thing odd. I'm hoping to have a reflection formula like this in support of that. But how do I know what this is a reflection through? And even worse, how do I know that this is a reflection at all? Is this actually a reflection? Well, it is. You can look at the geometry. So if I were to draw a little x, y, z axis system here, negating z is literally reflecting through the xy plane. So that's the kind of reverse engineering argument that I used anyway when I was coming up with this example to motivate thinking about the XY plane. Did everybody see how I strategized that? Okay, so that said, choosing this plane, this is my reflection, which I can plug into that function to see how the oddness works out. And of course, by design, this reflection plugs in, and this minus sign goes there as desired, and that gives me that minus sign, namely my needed minus sign. And again, integral zero by symmetry. Everybody good? Questions? Okay. All right. Okay, so moving along then. So we're going to make a little bit of progress in 5.6 here. We're not going to finish it quite, but this nevertheless is a pretty quick section. It's a bunch of applications, and this is not a physics class. So the physics applications, we're going to kind of, talk about a little bit. We'll show how the tools that we're using here can be, used in those cases. Anyway, okay. So I'm going to start off with what I mean by averaging numbers, which I know y'all know. All right. In fact, let me see if I can make my stylus work again. Are we back in business? Yes, we are back in business. Okay. So. If you want to average these 6 numbers, that's how you average. Okay, now, yes, I'm averaging 6 numbers, but you know what? I could make a different case here. Just a point of view. I'm kind of just averaging 3 numbers, 4, 7, and 8. Right? It's just that, the 4 appears twice in the numerator, and it also contributes in some sense twice to the denominator, right? And then likewise, you can think of the 8 as appearing 3 times in the numerator and contributing 3 to the denominator. So you can rewrite this whole thing. I guess that 7 is there once. We'll go ahead and do that. We can rewrite this whole thing like that. So it's just kind of an algebraic shorthand that when you're doing a regular old, good old, plain old average, repeated numbers can be streamlined by recognizing that we're really adding up kind of like so. Terms that all look like this. Right, that green term looks like that, the red looks like that, and the orange also, looks exactly the same. So think of this as just an alternative way to write how you average numbers if some of those numbers are repeated. Okay, is that cool? But it's still just a regular old plain old average. So now we're going to reinterpret a little bit, though, and I'm going to point out that, I could think of this still as 6 numbers being averaged, but if I want to return to this idea that I'm really averaging 3 numbers, it's just that 4 should count double because it is actually 2 of the actual 6 numbers I'm averaging. Right? So 4 should have a weight. What we call a weight of 2. And likewise, 7 has a weight of 1, and 8 has a weight of 3. So we call those weights. It's just a fancy way of saying how many times the number appears. And the numbers that we're averaging, right, the 4 and the 7 and the 8, those go there. Okay, so different point of view. So no longer going to think of this as an average, a standard average of 6 numbers. I'm now going to think of this as a weighted average of those 3 numbers. Is everybody still with me? Is everybody on board? All right, now modest observation. Having rewritten this with a formula, there is now no longer any particular need for these weights to be integers. Right, they were here, but I could free myself up and say, not all weights are integers, and there's no reason here for them to continue to be. So here is how we will use this to do an example. Y'all will recall, by the way, that in this course, the way course grades are going to be computed is by weighted average, right? And the midterm exams count for a certain percent, and the final exam counts for a certain percent, and attendance is a little something, and homework is something as well. So this is just an example of kind of how those weighted average calculations are going to go down. You can totally do this arithmetic yourself. So now, just to keep the numbers reasonable, I am using slightly more convenient numbers here. But you can see the weights that were given for our first three midterms, and hypothetical course here, the final. You can see those weights right there, just per the formula above. Right? And the numbers that we're averaging, so Bob's grades on the various graded items, here they are. Right? Again, just as per the above formula. And this is the arithmetic to be done to compute Bob's weighted average, which, if I punched it up correctly, is that number, which is a B. Kind of right down the pipe, B. Everybody happy with that thing there? Real quick observation before I go on. This, again, very analogous to how we're going to compute course grades in this course. If you're not 100% comfortable with your understanding of this idea of weighted average, or how grades are going to be done in this course, or what about this or that, whatever it is that you may be unclear about concerning how we're going to do grades in this course, just come talk to me in office hours. I'll be very happy to elaborate. I don't want there to be any confusion about how course grades are going to be done. So you're very welcome anytime. Just come talk to me. I'll clarify as much as you need. Okay. All right. Okay. What if we don't have a finite number of numbers to average? What if I have a continuum of numbers to average? Specifically, what if I want to find the average value of a function? And of course, a function, even if I just look, between A and B on the x-axis, there's still infinitely many values for the function. Right? So the big idea here to define the average value of a function is to use size in the domain as the weights, and you can see that right there in this expression. So if you have your interval, if you chop your interval up into little pieces, any little piece of size dx, the size is the weight, and of course the size of a little interval with dx is dx. Right? And then we are, of course, averaging the values of the function. And then you add up over all those pieces, which again in a limit turns into integrals, and bam, there you go. Here is our definition of the average value of a function. Is that cool? So now, of course, nice little convenience to observe that denominator computes really easily. That's just B minus A, right? So it's a nice shorthand, I suppose. You can go ahead and do that. And for memorizing purposes, I guess, sure, a case could be made that this is the easier form to memorize. For whatever it's worth, I find this formula here to be a little bit more natural, because I can literally see the weighted average right there and how that's written. Right? So again, it is, it's important to know the punchline. It's also important to understand where things come from. And I think this first formula, it's a little clunkier and bulkier, but I think it's better for intuition in that sense. Okay. All right, and an easy example, and I'm going to let y'all think through the details of this one, but averaging over the interval from 0 to pi, which of course has width pi. All right, and wanting to find the average value of this function sine x. And so we use this formula here to punch that up, and it turns out to be 2 over pi. Yeah? Okay. So we can use the same idea to talk about the average value. Oh, and wait a second. Am I out of time? I am out of time. Sorry. We're right at the bottom of a page. Oh, gosh. What did I just do? Well, anyway, it's definitely time to quit. Okay, so we'll draw the line right here. See y'all later. Have a good one.